Morning, students. Can you please write on the chat if you hear me as usual? Good morning. So, yes, very good. Okay, let me see how many we are. 13. I think we are all here. I can start. Very good. So, 1 second. I share my screen. But before I share the screen, I just wanted to make a brief introduction to make sure that you spent a good Easter break. I hope you did. My Easter break was fine. It was of course at home, but actually without the lectures I could also have some time to adjust to the situation because it looks strange, but actually we started the lockdown on March 8th, something like that, and after 1 month I didn't have still the time to adjust to the new situation in terms of personal setting at home, etc. And I still need to go to the office maybe tomorrow because I never went back to my office after March 8th, and I have some documents that I need to get in order to move forward with the lectures. Maybe tomorrow, we will see, because we are allowed to go to the office actually. For me, it's a bit more complicated because I'm not living in Bologna. I am in Reggio Emilia, it takes about 1 hour. So I think it's very likely that I get stopped by the police, but it's no problem. I can go. Okay, and I just wanted to make sure also, now coming to our future appointments, that you are there are, I think, 2 of you that booked the presentation for Monday. I think Emiliana and maybe Sam. I just wanted to make sure that you are ready on Monday morning to deliver the presentation. Just write on the chat if you are ready. I'm not sure if I remember well the names, but I think so. And I think they are only 2. But anyway, any of you that would like to deliver the presentation, a presentation like your colleagues did, just write on the chat. I think we can take 2 on Monday. Monday it's April 20, and then I think we can take if there are other ones. I think we should move beyond Monday. Monday max 2, because I want to keep in 1 hour the time that we dedicate to the presentation. So I see Emiliana Monday, yeah, okay. So as your colleagues did, I will, okay, and Sam, perfect. I will give you the rights to share your screen on Monday, and the first to, I don't know, you decide, but I would say first to Emiliana, who is the first who booked, and then to Sam, and then we have the discussion at the end of each presentation, like we did. I'm still thinking about organizing something at the end of the lectures to make a collective presentation with an organization, a structure that we could discuss beforehand. Maybe that you deliver an adjusted version of your previous presentations or a new one. I think it would be useful to make a final summary. And but we have time to discuss it. I just want now to share the screen to show you our calendar. So just 1 second, I'm sharing. So, okay, good. Let me also open Teams on the phone so I can check that you can see everything. Just 1 second. Okay. Very good. Let me put it here. And just 1 second, because I have the echo. I need to, okay, decrease the volume. So let me see if you can see my screen. Yes. So this is what you see here. It's our calendar, and actually it doesn't include the lecture that I did on March 23rd. So this is the calendar that you see here. Let's focus on where we are now. We are here, and we still have the full next week and the full week after that. And then we are still missing, if I'm not wrong, 3 hours. So we go to the end of April, and then I'm not sure I can teach on, let me see, what is the next date. So it would be, here it's April 30, and the next one would be May 4th. I'm not sure I can teach on May 4th. We need to take an agreement. And then, anyway, we are missing 3 hours here, and we will take an agreement on when to get these 3 hours back. In May, it will be. And maybe that we fix during these 3 hours our final presentation. We will see. In terms of schedule, I think I am fine, meaning that we still have 2 full weeks. And during these 2 full weeks, I have enough time to complete our calendar of lectures. So the schedule actually is fine, and so we don't have time constraints. I think I also already booked in Alma Esami. Let me just make a check, but I think so. The exams, and let me make a very rapid check together with you. Here is Alma Esami, and you see that indeed there is already the exam on the last 2 I am selecting are the exams that you can take, and it's, or let me see, yeah, okay, and the last 2, and these are June 10, June 24, as we agreed. As I told you, I cannot make exams before June 10, and the subscription is open from, let me see, it's open from, let me check, it's from May 4th. This is the date of opening of the subscriptions. I don't think you will be many students, so it's about 15, 20. So I think 1 day will be enough. Anyway, this is our perspective. As I mentioned to you, I cannot make exams before June 10. If you have any question about exams, please let me know. Let me keep the chat in the background so I can actually see if you have any question to ask. Just 1 second, I put it on the other screen. Here it is. Okay, good. And let me get the chat. Yeah, no questions so far. Very good. Okay, so now let's move forward with our lectures. Today I'm not making there is a question, Thomas. The university will not be reopened to students in June, so it will be a remote exam. It's an oral examination, as I mentioned at the beginning of this course. It will be done either through Teams or Zoom. I think it will be. It depends on how many you are. It can be also on Zoom. It doesn't make any difference to you because Zoom is accessible via web. And Zoom, with respect to Teams, has some capabilities to deal with many students at the same time. Usually I make the exam at 2 persons at a time. And what I do usually is the first question I ask the students to start by writing, and then we discuss orally. The exam is oral, but maybe that the first question I ask you to start writing. This is because it allows me to make the exam to 2 students at a time. So it's no problem. I have an exam, also an appeal in 2 weeks from now, in 10 days, where I have some 15 students. It's previous year's students. I am just trying remotely what is the best solution. I think the best solution will be, as I said, to make the exams at 2 students at the same time, and the first question you start writing, and then we discuss orally. And the way you present to me what you have written, I think I am trying several different solutions, but I think so far I used just the simple solution of placing the sheet where you have written your text in front of the webcam. Another solution may be that you take a picture of the sheet and send it to me. And other solutions may be that you write on a document, so with the keyboard, and send the document to me. But I think I will take the very simple solution that you show the sheet to me or you send a picture. I'm not concerned at all, and don't be concerned. If you have a poor connection, you just have to let me know, and then we can find other solutions if you are concerned by the connection. As I said, I am practicing. I am trying different solutions. Also, there is also a potential solution to make written examination through a new platform, but I'm not keen on that because you are not many students. I prefer to keep my habit of making the oral examination. If you have any more question on the exam, because I made an introduction at the beginning of the course and I explained how I carry out exams, it's also reported here. If you look on the page of the course, there is a description of the exam, and the description is unchanged. The only difference is that it's not in physical presence, but it's a remote exam. But this is my very simple way. Okay, so as I said, let's move to our lecture. Our lecture is, I think you remember, it's climate change and water cycle. We were discussing of this, and we started our discussion and we got about here natural variability of climate. So I just want to remake a very brief introduction. First of all, we had a question left by Maurus. You asked me about papers where to study something on the debate on the global warming and hydrological impacts, and I gave to you, as I said, one first paper, which is an example of an extreme view on the one hand. And the extreme view in that case is that the hydrological impact, it's not very substantial. And I mentioned that there are other views. I didn't give you reference for the opposite view, and I thought of it. I didn't check how long it is, but I think that a good reference for an opposite view and a very reliable reference is the sequence of the IPCC reports. IPCC Intergovernmental Panel for Climate Change. There is a web page, and these reports actually are quite long. So they are not papers, they are very detailed reports. And you should look at the last assessment report. The last assessment report, they are called AR. It stands for Assessment Report. The last is AR5 published. They are working on AR6. I suggest if you want to get a synthesis, because these reports are quite long, you may start by looking at the summary for policymakers. And just to give you an idea, let me open another web page. So IPCC on page. It's here. Just 1 second. It's okay. This is the web page, and reports. There is the link here. Reports, and here there is. You see that the synthesis report of AR6 is 2022. I think it's not published yet, but you can have a look. AR5, I'm sure it's already published, and so I suggest to look at the synthesis report, as I said, and I think under synthesis report there should be, because I think it is still quite long, I think there should be the summary for policymakers, and this is synthesis report, summary for policymaker. Usually this one, it's nice, and it's short, and it's nice for us because it's summary for policymakers means also summary that is useful to professionals, to engineers. And so the summary for policymakers is here. You may have a look at it. And this is a kind of established view. It's a good example of the other extreme, meaning that the IPCC is quite skeptical on skeptical, not skeptic. Skeptical means that it's quite pessimist on the impact of climate change on water resources, on the overall impact of climate change. But it is still balanced, so I think it is, and also it's very reliable. So I think it is a good counterpart for the other paper that I gave to you. The other paper is, Dimitris Koutsayanis is a well-established hydrologist, has a very good reputation, but on the other hand, he is skeptic on climate change. So I think also Dimitris Koutsayanis is a balanced view, but it's completely on the other side, and he criticizes IPCC a lot. So I think this is a good overview that you may take if you are interested on the debate. I just want to remind you, as an introduction to the continuation of my lecture, that there are several questions which are connected with the climate debate. It's not just one question. There are several of them, and they are not all controversial. There are only some of them that are controversial. And for instance, there is no doubt, everybody agrees that we are in a warming period. Everybody agrees on that. There is no, you can find people that also neglect that we are in a warming period, but this is really very, it's very infrequent, and also I would say not substantiated, not really well supported on the basis of scientific facts. And so on the fact that we are in a warming period, everybody agrees. If you look at the glaciers, it's a clear demonstration. There might be some parts of the globe where warming is not as pronounced. There are some glaciers in the world that are still growing in size, very limited ones. So one may say that it's not really a global tendency, but on the fact that on average we are in a warming period, there is no doubt on that. Also, there is basically no doubt that humans have an influence on that. So everybody basically agrees. So what are the controversial questions? A controversial question is to what extent human had an influence on that, because there might be other reasons leading to warming during this period. And this is something that is really interesting to an engineer, because, from a technical point of view, it's a completely different story if something is human-induced or not. Especially if you work on mitigation, it's a completely different story. And human-induced or not, I mean mainly human-induced or not. So basically, the controversy is to what extent humans have contributed to global warming. So contribution is accepted by everybody, but to what extent the warming that we observed in the last 30 years is due to humans? So if humans were not on the Earth, would we anyway observe a warming during the last 30 years or not? This is one first controversial question. And a second controversial question is related to what will happen in the future. It's related to the first one, because if it's human influence, then it's one thing. If it's a different cause for global warming, then of course the future predictions will change. So this is another question. What will happen in the future? And there are also sub-questions like will the warming continue with more or less the same behavior, or there will be tipping effect, tipping points? So these are relevant questions on which also climate scientists are debating a lot, because you can see different opinions in not only between different disciplines, but also in the same discipline like climate science. They are debating a lot on what will happen in the future. And the third controversial question, which is very relevant to us, is what is the hydrological impact of the warming? So is there an increase of floods? Is there an increase of drought? Is there an increase of something else or a decrease of something else? Hydrological impact is really a complicated question, and I will explain you why during this lecture. Temperature is relatively easy because it's easy to reconstruct for the past. Let's say it's easier to reconstruct, and it's also something that is more regularly varying. So this is the reason why temperature is relatively easy. Okay, so once we identified the key questions, now let's discuss now on the natural variability of climate. This is related to the first question that I mentioned. So to what extent are humans the cause of this the recent warming? And look, I will not discuss about politics and economics because I want to be focused on my field. So of course, when you go to the essence of the debate on climate change, there are, as fundamental drivers, politics and economy. And politics is not negative. I mean, it's something that is necessary in democracy, and it's part of our life. I'm not using the term politics in a negative meaning. It's fully, I mean, no implication on that. But still, I'm not experienced in this, and I have my opinions, of course, but I don't think it is relevant to us. So I will not speak of that. And then, of course, if you are very interested in the debate, anyway, you should also look at the political and economical implication, because, of course, this is fundamental. Another thing that I want to say before I go to the details, what happened in the last month is going to change forever our perspective on sustainability and climate change. Some of my colleagues do not agree. Some of them say, also in the scientific domain, some scientists say, no, it will go back to the previous situation quite quickly. But I don't think so. I think that the global emergency, the pandemic, has changed our priority in terms of threats, dangers to society. This is something that, I mean, even if virologists told us before that there was this risk, it was something that we didn't consider, and now we have to consider it. And besides considering, the pandemic will change many of the things, many behaviors of our life in a way that will have implications on our climate change mitigation policy, like reducing flights. This was considered to be a priority, and there was the need to convince people to reduce the flights. And the need was dictated by the fact that reducing emissions, and there was a movement that was trying to persuade scientists to avoid physical meetings because of the reduction of the flights. Now this problem is solved, and I think it is solved forever. I don't think in 5 years we will go back to the number of flights that we had before. I don't think that the next year scientists will start again meeting physically. We started remotely teaching, we started remotely meeting, And I don't think we will go back to the previous situations. So for some parts of this debate, the problem is solved and was solved by an external driver. I think it is extremely interesting to make this consideration. So, and also for other discussions related to climate change, which is, for instance, some economic implications. These implications will be completely changed after the pandemic. And as I said, this is my opinion. There are people agreeing with me, others who say, well-established scientists who say, no, in 2021 the situation will be back to the previous status. I don't think so. What I want to tell you is that I think on one way, on the one hand, you may think that you are suffering from this situation. On the other hand, I want to tell you one thing that I already said, and I'm also telling to my colleagues. I think we need to be very forward-looking. We don't have to be pessimist. My vision is not pessimist, but I think that we have to be forward-looking and trying to understand, try to refine our education and your personal study, trying to predict what will be the main task, the main challenges for engineers in the future. And I don't think it will be mitigation of climate change. This is because this is what I believe, because I think many of the actions will be automatically taken. I give you another example and then I start teaching. In my city, there was a debate on the air pollution. Air pollution was really in the headlines because we are one of the most polluted cities, Reggio Emilia. It's a small one, but in the center of the city, there is a concentration of PM10 particles that is above limits during the whole winter. And there were a lot of discussions like what can we do and economic implications, a lot of consulting activities that were commissioned, and the people were working for about 10 years on that. Now the problem is suddenly solved and I don't think we will go back to the previous concentration of PM10 even during the winter, because we already know that during the next winter, for instance, many people will work remotely and many students will go to school remotely. So you may say this is only for 2021 and then it will pass. I don't think so. I think that once that many people also in the public administration started to work remotely, I don't think we will go back to the previous situation. There will be other problems, like how to control people that are working remotely, how to stimulate them, how to make sure that they then don't lose their social connections. But on the other hand, I think that our experience during this month have clearly shown the way. So I don't think air pollution will be a problem next year and in the coming years in my city. But of course you may disagree, but what I want to tell you is just keep your eyes open, because I think there is room for driving your education in the next couple of years in a different way, and we have to try to understand. I will do my best to help you in this. I am already thinking on how to change my programs for the next year. The program of my courses, the table of content, because I think we need to change it. There are some problems that are not problems anymore. Anyway, studying the natural variability of climate, discussing it is still very useful. And we know that climate is naturally variable. We know that because we studied already in the primary school that we had glaciation in the past. I think it is useful to look at these past fluctuations of temperature. And this figure is a good start. I'm sorry. This figure reports the progress of the main glaciations and up to about 500 millions of years ago. And if you look at the blue line or the black line, these are moving averages of concentration of isotopes in the atmosphere. And this concentration of isotopes, it's an indicator, a proxy for temperature. it's not temperature, but to give you an idea, any change, any unit change of parts per thousand, look at the scale of the y-axis, any unit change on the scale of the y-axis is about 2 degrees of temperature. So you can see that during glaciations the change of temperature was about 4 parts per thousand, the extreme. If you look at the blue line, is something more than 4. So the changes of temperature, global temperature, that were induced by the glaciation is in the range 10 degrees of temperature. And keep in mind that when we talk about global warming, we are talking about 1 degree of global warming in the past 150 years. So trying to understand, or at least trying to get a picture of these changes is helpful to get an idea of what it means, a change in temperature of 1 degree rather than 5 degrees. And if you look at this graph, you see here 4 glaciations. And glaciations, you have to look not at the high peak. High peak is high temperature. You have to look at the minimum. And you see here 4 minimum, which correspond to 4 glaciations. If you go back in the past, we can find traces of other glaciation in the more far past, so beyond 500 million years ago. The gray band is uncertainty in the estimates, which is increasing as you go far in the past. And from this figure, you can see that we are in a glaciation now. And we are in actually in the Quaternary Glaciation. And let's look at the link which is shown here, because this is something that I think we need to make clear, the fact that we are in a glaciation now. And if you look at the Quaternary link, Quaternary Glaciation, there is a nice description. This is a Wikipedia page. And there is a nice description. I think it is a description that is suitable for our purpose. We are not studying the scientific details. If you want to study the science of something, Wikipedia is not a good reference. But if you want to take a story, if you want to take this story of the phenomena you are interested in, Wikipedia provides you a good introduction. And so the Quaternary Glaciation, as you see here, is an alternating series of glacial and interglacial periods during the Quaternary. It's a period that began about 2.5 million years ago and is ongoing. So this is the essence of what we have to get. 2 things we have to get from this sentence. First, we are still in a glaciation, but within this glaciation there is, I'm selecting, an alternating series of glacial and interglacial periods. So let's have a look at the progress of temperature during the Quaternary Glaciation. This is like a zoom. If you click on interglacial, the link interglacial periods here, and you click on this link, you get a figure there, which is an interesting zoom. Here you can see we are talking about thousands of years ago. So let me go back to the previous picture of the glaciations. Here we are. The figure that I just showed you is a zoom on the extreme right part of this picture. And look, on this picture that is on the screen now, if you look on, just 1 second, let me put this figure here so I can write on it. Give me 1 second. I'm not writing on the blackboard, so be patient. So if you look on this right part, let me use red because we put some life. If you look on the right part here, I am looking in a range that is about the last 50 millions of years. I want to make a zoom on the very right because the figure that I showed you before, which I'll show you in a second, refers to this very far right. And you don't see any fluctuation here. If you look at, for instance, the blue line, you see we are now focusing on this part, which I will explode, and you will see in the zoom figure several fluctuations which you don't see here. Why we don't see them here? Because this is a moving average. And if you look, I think, let me see the caption. The blue line in figure 5, read here in my site, sorry, I increase it, is a short-term average, which was constructed by applying a weighted moving average over a period of 3 million years. So we don't see any fluctuation because of the moving average. The moving average is over 3 million. So now I move to the next figure, this one. Here you see the fluctuations, which disappeared in the previous one for the moving average. And these are, Epica and Vostok are two reconstructions of past temperature. They are quite coherent. They are not equivalent, but they are quite coherent. And they are reconstruction based on proxy data. I think they are ice cores. If you look at the Wikipedia page, there are the details. I'm not interested in these details, and I will never ask you at the exam these details. But what's important to see is here you can see the temperature in scale. And if you look at the past 1,000 years, you see that there was a low temperature period, which is let me increase the size, which is, if you look at the Epica, let me copy this image and, sorry, let me copy this image and paste it here. So, now, if you look here, in this period, we had a low temperature period. It's extended from about 11,000 years ago up to something like 120,000 years ago. And then, starting from 11,000 years ago, we had an increase. So this period here, you see, it's the recent period. Started about, as I said, 11,000 years ago, we had an increase of temperature. This figure, it's all included in the glaciation, the Quaternary Glaciation. And what you see here, in terms of up and downs, it's glacial and interglacial periods within the glaciation. So the red circle is a glacial period, which we sometimes call the last glaciation. And it occurred up to, as I said, 11,000 years ago, and it lasted about 100,000 years. And then there was this increase. So now we are in an interglacial period. So it's a period which is characterized by regression of glaciers. And we know that because we know that since the last glacial period, we have a retreat of glaciers that originated several lakes, etc. And also originated this retreat of glacier, a very important erosion of the mountains. So it changed the shape of the Earth crust radically. But this is only the last part of a long story which is characterized by glaciation, and we are still within a glaciation, and and glacial and interglacial periods within the glaciations. Just to give you an idea, we define a glaciation with the presence of ice sheets over the Earth. And now we have ice sheets at the North Pole and South Pole, and also in some parts like Himalaya we have, and also some parts in the Alps, very minor. In the Alps we have perennial glaciers. In the past, there were periods where we didn't have any ice on the Earth. We know this, and this is a known story, okay? Just keep in mind that a relevant question here is whether the current warming is occurring with a pace that is unprecedented. So these changes, which I'm showing to you now here, occurred in thousands of years. Now we are talking about global warming, which occurred in 30 years. So it's a different, maybe it's a different pace. Scientists are discussing on that. On the other hand, there is to say that the warming that occurred in 30 years, it's 1 degree, not of the order of magnitude of, you see changes here of about 10 degrees. And so it's an order of magnitude that is of course different. Okay, now let's go back to, let me close this 1 second. And let me say that it's still not clear to us what caused glaciations. There are several hypotheses, and the hypothesis may be that the presence of dust in the atmosphere, which may be due to eruptions, may have caused them, or it may be the changes in the orbits. There are some theories that postulate that changes in the orbits, even of the sun, may have occurred, and also the orbits of the Earth and the Moon. These are also possibilities, but it's still not very clear to us. Now let's look at the very recent past, and this is 2000 years ago, so it's a different scale. We already saw this picture. In the very recent past, you see fluctuations that are not as large, but still you see some fluctuation, and in particular we discussed the medieval war period and the Little Ice Age. So indeed, if you look at this picture here, it seems that the warming that we had in the last 30 years it's occurring at a pace that is unprecedented, but this is unprecedented for this time span. And also there is to say that these reconstructions give to you an average picture. It's when you reconstruct the temperature, I already mentioned this to you, through proxies, you get an estimate of the average, and it's like a moving average. Instead, if you look at the black line, these are observations which are averaged over the globe but not in time, and this is why you see that the fluctuation is more pronounced. And if you look at the past, the fluctuations are less pronounced. Still, it seems that during the medieval warm period, in fact, we have some witnesses which were taken in the archives of the monasteries, and also there are some witnesses that are orally how to say, vehiculated to the forthcoming generations, which seems to indicate that the woods in the Alps were extended to a higher altitude with respect to now. But of course, there is always uncertainty in that. But still, there is agreement on the presence of this medieval warm period when the temperature was probably comparable, at least in Europe, to what we observe today. At least in Europe, because it's not clear whether the medieval war period was also there in the Americas and in other continents. In Europe, we have the fact that we have the support of these witnesses, but in other continents, we don't have any documental support of this. Now, an important thing to mention is the fact that it's known that several geophysical variables and several environmental variables have fluctuations, are characterized by fluctuations. And there are several proofs for this. And one is the progress of temperature, which I shown to you. And other proofs are given by, for instance, the level of the Nile River, and I'm moving to hydrology. The level of the Nile River as it was observed by the Egyptians, they collected observations for about, if I well remember, 600 years, about 3,000 years ago, and we can see there fluctuations. Fluctuations not seasonal, I mean multi-year fluctuations, multi-year cycles. And there has been a term that is been coined by statisticians and hydrologists to identify the presence of fluctuations in geophysical variables. And this term is, let me expand the font, the Earth effect. I am making a selection. And this is an effect, as I said, that was termed to characterize the presence of cycle in a geophysical time series. Later on, again, Dimitris Koutsoyannis proposed to change the name to Ernst-Kolmogorov. And Ernst-Kolmogorov, because I tell you the story, the Ernst effect was named after Harold Edwin Ernst, a famous hydrologist. He was British, who was tasked to design a series of reservoirs along the Nile River. And he discovered this effect by analyzing precisely long-term observations of the Nile River. But later on, Dimitris Koutsoyannis realized that also Kolmogorov, before Ernst, identified this effect on different variables, not geophysical. But Kolmogorov was Russian, and for this reason, his discoveries were not, let me use this game of word, his discoveries were not discovered in the short term. They were discovered, people realized many of Kolmogorov's discoveries only after a while. By the way, Kolmogorov was really a brilliant scientist. He would deserve to be more known. He died relatively recently, I think 1979, and he made really a lot of contribution in math and with applications. It's really a scientist that was really brilliant. And then Koutsoyannis proposed to name it Ernst-Kolmogorov, but this is not relevant to us. I mean, it's just a matter of terminology. And the term that is widely known is Ernst effect. And it's interesting to note how Ernst discovered it. Ernst was studying the optimal capacity of reservoirs to make a compensation of river flows. So the purpose of Ernst was to transform the Nile River flows from a fluctuating in the year, within the year series, and it's fluctuating within the year for seasonality. He wanted to transform it in a constant series. And you can do it with a reservoir. If you build a reservoir, you store water when there is abundance of flow, and then you release water when there is scarcity. So you make the outflow regular. And of course, you need a certain storage capacity. And it's intuitive, it's your intuition that if you have high variability during the year, if you have high seasonality, you need more capacity of the reservoir. So Ernst studied the optimal capacity, and he was expecting that by increasing the number of the years that he was analyzing, the capacity remained more or less the same. Like once that you estimated it for 1 year, you go to the next year, and given that seasonality is expected to be more or less the same, you get more or less the same capacity. Maybe that in only 1 year you have some uncertainty, but if you get 10 years and then the next 10 years, more or less you get the same capacity. Ernst realized that the capacity was continuously increasing. He was increasing the number of years, 10 years, 20 years, 30 years, and the capacity kept increasing, the optimal capacity of the reservoir. So he didn't realize why. He was astonished, like why this happens, because I am expecting that if I increase the number of the years, I get to a steady estimate. But actually, if you think at it, if you have a long-term cycle, so if you have an up and down of the river flow that is extended over more than, let's say, few years, indeed, you get an estimate of the capacity that is always increasing, and always increasing up to the cycle period. You have to get a time span that is higher than the cycle period in order to stabilize the storage. So Ernst realized, after thinking at it a lot, he realized that the reason for the increasing capacity was the presence of long-term cycles. And this is why they called it the Ernst effect. It's a very interesting story. And so for the first time we discovered that indeed there are these long-term fluctuations, even in river flows, in many geophysical variables. And indeed, you can see here, this is a picture, it's a rotating picture of the Po River flows. It's a smoothed picture. I did it with R, by the way. It's quite easy to do it with R. And on my website, there is also the R code for drawing it. It's smoothed, and you have, it's a 3D because you have years on one horizontal axis and days on the other horizontal axis. And this picture allows you to see that indeed there are long-term cycles. Look at the drought period. The drought period is during the summer. If you look at the days, you see that the drought, the red part of the picture, is around, let's see, let me do one thing. Let me stop it, because if we keep the figure rotating, it's not easy to see it. So let me stop it, just 1 second. Okay, here it is. I copied it, and let me paste it in the graphic program. Okay. So look at the red part, and let me take, as usual, I think the optimal color here is the blue. So here is the drought, the summer drought. Okay, and you see the days, it's about 210, which means July, more or less. July, August. Usually the drought in the Po River starts, let's say, mid of July up to end of August, the summer low flow period. But actually you see that if you look at the summer and you look at the progress of the years in the other horizontal axis, there were some periods where with less water, some, let's say, more red period. And a first one, very pronounced, was this one here. Let me take the yellow. Look at this period here. This is an important drought. It was observed in all of Italy, extended from about 1943 here up to 1960. And this is well known. It was an important drought. It started during the Second World War, and it's still poorly studied. I mean, it's not well quantified. It is well known because people remember it. And then there was another one after the year 2000. It was from 2003, because this series is extended up to 2007. And you see that just before the year 2000, and then in 2003 there was a huge drought. This is another period that ended because after 2009 the summer flows of the Po River are not so low. And I have an updated figure, but I need to, it's not yet uploaded in my website. So indeed you see these periods, and also there is another high flow period here. It's around 94 2000, we know it. This is a series of two very important floods in the Po River which occurred in 1994 and 2000. And the one of the 2000 was a two-peak high flow, October and November. And also look at this period here. It's a period, shorter period of high flows in June. And what is even more interesting is this peak that completely disappeared. This is a high flow period. This hill here completely disappeared recently. It's a high flow period in March, maybe probably due to snow melt in the Apennines, which it's under global warming, it's much less influential on the flows. Anyway, you can see cycles here. So it's another demonstration that indeed we have this variability, this natural variability, and therefore it is something that we have to take into account, and it's not easy to estimate it because we don't know the causes of this natural variability. So basically we cannot really say if there is now natural variability that explains at least part of the recent warming. Maybe, maybe not, and it's not easy to identify this because as I said, the causes are not known. Let's also say that before global warming, there was a period in the 70s and 80s of cold weather, and this period, I'm moving up in my web page. This period is the period of the so-called global cooling. And it's also another interesting connotation. If you click here, there is a Wikipedia page which describes this global cooling, and it was, as you can see here, during the 70s, it was a conjecture of imminent cooling of the Earth, culminating in a period of extensive glaciation. It's interesting to notice that the term climate change started to appear in the 70s, and it was Kissinger who first mentioned the climate change in the political arena, and it was created this term to mean the global cooling, and then of course extended to the global warming. It's another interesting connotation because it's an example of the presence of variability, and in this case it seems that global cooling was caused by an increase in the aerosol concentration in the atmosphere, which may be due to a temporary effect which is not yet explained. Okay, let's go back to our discourse. After discussing natural variability, now let's discuss the human influence, because this is our central discussion. And before we move forward, I suggest that we make a break of 5 minutes, if you agree. If you have any question, just let me know. Okay, so human influence. Let's start with what we know for sure. And what we know for sure is that in the urban context, human has a great influence on climate. And this is proved. So at local scale, there is no doubt that there is a strong human influence. And the heat island effect is the term that is used to identify the warming in the urban context. It is called by heating and cooling during summer in cities, and it's also caused by the reflectivity of the urban context, which is less green than the outside, than the outside fields, and therefore has more emission of radiation. It's also given by the fact that wind is relatively weaker in the urban context. So the result is something that developed during during the last few decades and is indeed very relevant. Is something that if you are used to drive a motorbike, you can really perceive a difference which is in some cases may be extended to 2-3 degrees of temperature. It depends on the scale of the urban settlement. Also, we know that in the urban context there is an increased concentration of pollutants and aerosols and tiny particles. So there were measurements that prove that in the urban context, as I said, the temperature may be 2-3 degrees higher than the outside fields. The heat island effect, on the other hand, is a local effect. If we look at the global context, we know that the increase of concentration of greenhouse gases is supposed to have induced a global warming. And the way we can study this phenomenon, we have two ways. There is the deductive approach, which makes use of global models, and there is the inductive approach, which is based on the analysis, on data analysis. Let's say that if we base our consideration on a deductive approach, there are simulations by climate models that show that the increasing concentration of CO2 in the atmosphere after the Industrial Revolution may have induced a global warming which brought the global temperature at more than let's say around 1 degree above the pre-industrial level, and may bring it to more than above 2 degrees centigrade by 2100. So the warming that we also observed is about 1 degree, but the simulation by climate models based on emissions of CO2 scenarios show that the temperature may increase more than 1 more degree. So we could get to +2 or above. You know that there are some targets, that were fixed by the Paris Agreement to contain the warming to +1.5. It seems, according to the simulations of the models and according to the current progress of emissions, it seems that this target is hardly attainable. Now, what is the implication of this warming? It's not just a matter of temperature, because you know, if it was just a matter of temperature, one may say, okay, this is a change that is occurring rapidly, so this is an additional problem. On the other hand, a change in temperature already occurred in the past. It will cause migrations, it will cause changes in the political setting, it will cause changes in the economic setting. On the other hand, there will be probably lands that cannot be cultivated anymore, but there will be additional lands that will become available for cultivation which cannot be cultivated now. So it may just imply, if one just look at temperature, it may just imply a change of settlements, a change in demographic concentrations, in demographic increase. But if it was occurring in the long period, there wouldn't be, I mean, it could be also sustainable. There is, of course, the concept that is occurring in a short period, and this is something that makes adaptation more difficult. But on the other hand, there is also to say that it's not only temperature, because there are implications in natural hazards, implications in other variables, which are typically hydrologic variables, which are water resources availability and flood hazards, drought hazards. These implications are really concerning because these implications are occurring in a context that is completely different with respect to the past. If you look at, for instance, at the number of people that are now living on the Earth, it's like I think that if you go back to 100 years, our population was like 1/3 with respect to now. I don't have the numbers in my mind now, but it is astonishing the increase in population that we experienced in the past 50 years. And then, I mean, the implications in terms of natural hazards would be implications that have an impact that is more significant with respect to the past. Now, how can we estimate these implications? I told you that this is another big question mark because actually the effect of global warming on flood frequency, on flood magnitude, on drought is still very uncertain. And let me summarize to you some of the studies that have been conducted so far. So first of all, let's look at the theory. The theory says that if you increase the temperature of the atmosphere by 1 degree, there is an increase of in the saturation vapor pressure of about 7%, which means that the atmosphere can take 7% more water in the form of vapor per each degree of warming. It means that with respect to the pre-industrial period, now we have 1 degree above of global temperature. It means that on average, the water content in the atmosphere, the water storage capacity of the atmosphere is increased about 7%. This is the potential storage. So if you assume that atmosphere is saturated when extreme event occur, then it looks like you have 7% more water stored that can cause violent storms, can cause floods. Of course, there are some things to be kept in mind. So if the saturation vapor pressure is higher, it's not automatically implied that the water content is higher because, you know, evaporation should also increase. So in order to saturate the atmosphere, if you have a higher storage capacity, you need to get a higher evaporation. But actually, it seems that evapotranspiration decreased under global warming, originating the so-called Evapotranspiration Paradox. And it's not yet explained. So it's not yet explained why evapotranspiration is decreased under global warming. There are several explanations. The first is, for instance, maybe that evaporation is measured in pans. So it's measured by letting water evaporate in small tanks. Now, it may be that around the tank you have an increased evaporation from the field because these tanks are usually placed into fields in order to refer to an undisturbed situation. So it may be that around the tank, around the pan, you have more evaporation from the field, which limits the evaporation from the pan. But actually, the several measurements that were taken seems to contradict this hypothesis. It may be that once evaporation increases, you have cloud formation, and cloud formation, of course, reduces the temperature, and therefore you have less evaporation. It may be that wind velocity is decreased. On the other hand, it's a fact that evapotranspiration is not increased, so we cannot say for sure that we have more water in the atmosphere with respect to the pre-industrial level. This example that I already gave to you is an example of what is called a climate feedback. And this is a very important concept that you have to keep in mind. The feedback is, I'm reading here, the feedback is the process in which changing one quantity then causes the change of a second quantity. And the change in the second quantity in turn changes back the first quantity. So it's feedback. The positive feedback amplifies the change in the first quantity, while the negative feedback reduces it. So an example of negative feedback is what I just mentioned. You have an increase in temperature, global warming. It causes an increase in evaporation, and then an increase in clouds, which reduces the warming. This is a negative feedback. It's like a compensation. The negative feedback can be, for instance, that if you have warming, you have evaporation, you have a reduction of the lakes, extension of the lakes. Think of the Lake Aral. The Lake Aral, there was a warming, a reduction of the extension. The reduction of the extension of the lake causes a reduction in evaporation, which means a reduction in rainfall, which means less river flow going into the lake, and therefore further reduction. So this is a negative feedback. And of course, we are concerned by, this is a positive feedback. We are concerned by positive feedbacks. Negative feedbacks is like compensation. So you make a perturbation, like you pollute a river with organic matter. If you pollute a river with organic matter, you have an increase in bacteria which degrade the organic matter, and after a while the river is clean back again. After the organic matter was degraded, the bacteria die, and the river goes back to the previous situation. This is an example of a negative feedback, compensation. Now, there is to say that if nature is there, and if humans are on the earth, it means that they are resilient, because the nature and humans, like living species, are the result from a natural selection. And also natural processes are the result of a selection. And of course, if natural processes are there, is because they are resilient. Resilient means that there are feedbacks. So it is, we know for sure that climate is able to compensate to some extent, in the same way as we know for sure that a river is able to compensate to organic pollution to some extent. So the fact that, again, a natural system is living, is there, it means that there are indeed negative feedbacks. And so the problem is to know them and to quantify them. That there are several feedbacks that we still don't know, and evaporation is one of these. We still don't know why really evaporation reduces under global warming. So these feedbacks are part of our uncertain knowledge of the climate system. This is another thing that we have to take into account. There is sometimes we have the feeling that we know everything about the Earth system and the climate. Actually, it's not like that. And the demonstration is that very often hazards get us unprepared, like the pandemic. The pandemic, we were not prepared. And the reason is that, you know, we still have a little knowledge of this virus. The same thing is for climate. And now, as I said, there is this feeling that is diffused in the public that we know climate, so we can predict what will happen. Actually, this is not true. There are many things that we don't know, so we can make predictions, but they are uncertain. And uncertain in this case is due to lack of knowledge. So the main message is then let's concentrate, let's try to understand these feedbacks, because these are causes of uncertainty. And the main message is that I'm delivering now is, look, we have models, and we will discuss them later, that allow us to make predictions, but these models are uncertain. And as an engineer, you have to be very concerned by uncertainty, because it's your responsibility. So if you make a design and you make a mistake, I mean, it's your responsibility. So really, you have to be interested by uncertainty. You have to be interested by the risks. And look, it's not just enough that you use safety factors, because safety factors, again, have to be estimated on the basis of a knowledge of the underlying uncertainty. So, to what extent the humans are to make a conclusion, are affecting climate? There is uncertainty. There is uncertainty, and the reality that you get if you use a deductive or an inductive approach is different. And we need to discuss this. We need to look in more details into the differences, by taking into account that the deductive approach has a limit, of course, which is our incomplete knowledge of the system, but potentially has the great advantage that may allow us to make a prediction by taking the physics into account. So if there are tipping points, if there are threshold effects, with a deductive approach, we may be able to estimate it. So let's look at now at the variables, at the data, because this is a good point to start. And then later on, we will describe climate models again. Precipitation. So precipitation, is it changed under global warming or not? So actually, precipitation is a different variable to describe. With respect to temperature, it is much more difficult. What is the reason? The reason is heterogeneity and a variability in time that is much more pronounced with respect to temperature. Heterogeneity refers to variability in space, and also with respect to temperature, precipitation is much more variable, and also there is the variability in time. So it's a very local effect, and it's not easy to estimate changes because variability is so pronounced. So let me just start by saying that it's difficult, but nevertheless we have to find some indication, because it's our task as engineers. We have to be able to understand if there was a change or not. Okay, here there is a figure which shows to you the long-term mean precipitation by month, which is a good indication of the spatial distribution of precipitation. It shows what we know already. In the highest precipitation is on the equator, and then if you move far from the equator, you get a decreasing trend, which a kind of variability which also depends on the season. Okay, basically this is what we already know, but the question is it precipitation increased, changed or not? First of all, there is a discussion on the decline in pine evaporation. I already discussed it. And again, let's take into account that it seems that evaporation is not increased under global warming. So now let's look at precipitation. So precipitation, if you look at the global average is not changed in the past 30 years. It's more or less stable, and more or less stable with an average value of global precipitation of about 1 meters per year. And again, this is quite stable. But of course, if you look at the spatial distribution, there are changes, and these changes basically are depicted by several studies, and several studies agree that the precipitation amount has generally increased over land north of 30° north and from 1900 to 2005. So there is an increase in the north, but precipitation has declined over the tropics since the 70s. Globally, as I said, there has been no statistically significant overall trend in precipitation over the past century, even if trends have varied by region and time. So it seems that the eastern portion of North and South America, Northern Europe, Northern and Central Asia has become wetter. Conversely, the Sahel, the Mediterranean, Southern Africa, and parts of Southern Asia have become drier. Over the continuous United States, total annual precipitation increased at an average of about 6.1% per century since 1900. But there are regions where there is a decrease. Hawaii is a region where there was a decrease in rainfall. And I mean, we don't have enough information to be able to say whether these changes are part of a cycle that may last for 100 years or not. Now, let's look at extreme events. Extreme events, I co-authored a global study on daily averages. And in a nutshell, this global study, we considered about a total amount of about almost 70,000 stations with at least, I think the years of record is at least 50 years. And by adopting, if I well remember, 68,000 is for a duration of 30 years. For a duration of 50 years, it's, I think, is something like 30,000 of stations that we analyzed. 50 years is quite a long period, extended from 63 to 2013. Again, we focused on daily precipitation because for daily precipitation you have it's the max, it's not the max, it's the amount of rainfall that we get every day. For daily precipitation you have a lot of observations. What we found in a nutshell is that you have an increase in frequency. The increase in frequency, you see this picture here, and look at the upper part. GL stands for global, while NH is northern hemisphere, and the reason is that in the northern hemisphere there has been a change that is more pronounced. Now, here you see that there is a change in frequency. This graph is basically showing the frequency of rainfall, and I don't go into the details. There is the link to the paper if you're interested, and I think it's not here, it's on my website actually. I have to put the link here actually because it's already open access, so I think, I'm not sure if it's already open access or not. I think so, but maybe that it becomes open access after 2 years. It was published 1 year ago. Anyway, the figure showed the increase in frequency. The increase in frequency, it's about over, and this refers to a long period, and then we focused on a shorter one. In any case, you see that there was an increase in frequency of about 20% in the past 100 years. 20% seems to be like a huge increase, but actually, you know, if you have one extreme per year and you pass to 1.2 extremes per year, it's not really a lot. And also frequency means I mean, once that a system is resilient against a given intensity of rainfall, if you get one event, or even if you got one event and a half, it doesn't change much, because what we found is that the intensity of the daily rainfall is not much increased. This is not the we found a slight increase, but it's not statistically significant. On the other hand, this is the daily rainfall. We have some intuition that suggests that the increase in precipitation may be occurred over short-term precipitation, like 15 minutes precipitation, something like that. And it becomes indeed more difficult because we have less data. If you look at sub-hourly precipitation or hourly precipitation, the amount of data is much more limited with respect to daily precipitation. But still, there have been several studies conducted on hourly precipitation, which refer to selected regions. And what has been found in some cases, the results are not always coherent, are summarized here, basically, in this paragraph. And what has been observed, as I said, the results are not coherent, but in some regions, they found that indeed extreme precipitation seems to be increased in intensity according to the Clausius-Clapeyron rate of increase, which is, as I said, 7% per degree of warming. So in some cases they confirmed it. There was one study on one region in Australia where they found a higher increase, which is about 3 Clausius-Clapeyron, which means 18% increase in intensity. Now, from the point of view of hydrology and engineering, if you talk about an increase of 6% in extreme precipitation, it's not really a big increase. It's not something that may justify a significantly increased risk. If you talk about 20%, it's becoming something relevant. So, but if you get in 1 hour, typically in Italy, in Bologna, if you look at the 1 hour precipitation with a return period of 100 years, which means an extreme event which occurs on average every 100 years, and you look at the duration of 1 hour, it's about 50 millimeters per hour. So this is an example of an event in Bologna that may occur on average every 100 years. If you turn from 50 to 54, which is an increase of 7%, it doesn't change much. And it is not a really big change. If you turn from 50 to 60, it may be something relevant. So it may be that with an increase of 20%, you get a flood, while in the original value of the variable, you wouldn't get any. This is possible. But if you look at the 60% increase, it's not really relevant. And it is not sufficient to justify the fact that recently we observed many more floods than in the past. So indeed, if you look at the data on floods, in the past 20 years, all over the world, we observed many more floods than in the past. But the justification cannot be only a 6% increase of extreme rainfall, especially if you think that daily rainfall is not increased. So it doesn't look like the increase of floods is justified by the trend in rainfall. Okay, and just let's say that usually these changes are detected through a trend analysis. And the trend analysis, it's usually done by assuming a linear increase, linear trend. So it's a linear regression. And the reason why we choose linear regression is that it's more robust, it's less uncertain, if you take an exponential regression with the reduced amount of data that we have, you get a lot of more uncertainty. On the other hand, you still have some uncertainty even in trend analysis. So this is something that is to be taken into account. You may think that Professor Montanari is always mentioning uncertainty, so what conclusion should I get? I will tell you the conclusion later on, okay? Okay, now let's go to sea level, which is another variable of interest. It's not very interesting for us, but it's something that is a matter of concern today. I want to make the long story short. First, there is an excellent open access review provided by Judith Curry, which is an excellent source. It's the source of much of the content of this section. I invite you to, if you are interested, to visit the blog of Judith Curry. Judith Curry is a very well estimated scientist. She's known to be, let's say, I am improperly using the term climate skeptic, improperly, but anyway, she's known to be one of the scientists who are more skeptic about the reliability of climate prediction, but she's very well respected. It's, I would say, something like Koutsoyannis. Both they are very well respected. On the other hand, they are a bit skeptic on the real reliability of the climate predictions. With respect to Koutsoyannis, Judith Curry is much less provocative. Koutsoyannis is provocative. She's not. So I think it is indeed a very interesting reference if you're interested in that. Also, Judith Curry is involved in policy making and design. So she's concerned, as we are, about uncertainty because she's a consultant and therefore she was a professor. Now she is a retired professor and she's a consultant. So she's much concerned, as I said, by uncertainty, and for this reason she's really looking deeply into it. And for this reason I think she's a good reference. Now, as I said, I want to make a long story short. This is a progress of sea level rise since the last glacial maximum. You remember I said that the last glacial period before the current interglacial period started. So the last glacial period ended about, I said before, 11,000–12,000 years ago. Indeed, you see the correspondence in terms of sea level rise. So we had a sea level that was in the glacial period about 120 meters lower than today. I say again, 120 meters lower. And then with the melt of the glaciers, sea level raised. If you look at the recent period, let's see what happens later, okay? But in the recent period, you see that it flattened, okay? Now, this is another picture, same thing, okay? More or less same thing. Now, the recent period, here it is. This is sea level rise from 1880 to today. It's quite a steady increase, and indeed it's raising. It's raising starting from the end of the Little Ice Age. It's raising due also to the warming, because when you have the warming, you have a melting of the glaciers and an expansion of water, which are both contributing to raising sea level. Keep in mind that measurements of sea levels are very sparse, and they were actually very sparse up to 1992, when the measurement with satellites started. Now we are measuring the sea level with satellites, and this is much more reliable. On the other hand, there is the question of comparing the observations that are taken by the satellite with the ground observations. Keep in mind that a similar problem we have when we compare temperature retrieved by satellites with ground observations. And for temperature, there is an additional component which is related to the fact that the measurement is done in the troposphere and not at the ground with satellites. On the other hand, when you compare temperature measured by satellites, the rate of warming is lower than the ground rate of warming, probably for the heat island effect. More or less the same thing here. But look at the more interesting thing that I wanted to emphasize. What is the amount of sea level rise from the pre-industrial period to today? It's about 15 centimeters. Okay, if you start from 1880, it's about, let's say, 1520. This is the range. So we are not talking about meters, and it's very much important that we keep the order of magnitude into account. And also notice that the trend is quite stable. And this is recent sea level rise since 1992 during global warming. And here you see that again, it depends on the average you look at, but we are talking about an increase according to this satellite. We are talking about an increase from minus 12 to something that is around 15. So here it seems that it's if you look at the linear regression, it seems that it's higher, but again, this is satellite measurements. So let's look at the conclusion of the fifth assessment report, which is, as I said, it's a well-respected conclusion and it's on one of the extreme sides. It is very likely that the mean rate of global averaged sea level rise was 1.7 millimeters here between 1901 and 2010, and 3.2 millimeters here between 1993 and 2010. So if you consider 3.2 millimeters per year, it is about in 10 years 3.5 centimeters, which is in 20 years 7 centimeters. And it is concluded here it's likely that similar high rates occurred between 1920 and 1950. So, I mean, it's not a huge increase, but there is the problem that for the future, there is the problem of the tipping points. And let me now go to the predictions. The predictions which are done with climate models. And let me go down here to this table. So these are the increases predicted from now. Now it's IPCC AR5, so it's 2015. So predictions of increase from now for temperature according to the different scenarios. And the first rows in yellow and white, the first 4 rows are increasing temperature with respect to different emission scenarios. RCP 2.6, RCP 0.5, it's emission scenarios. RCP 0.5 is an extreme. It's business as usual. It's an extreme. And it's in temperature, we are talking about 2 degrees and 3.7 up to 1900. Now let's look at the sea level rise. The extreme is 0.6 centimeters. Again, we are not talking of meters. 0.6 centimeters, it's an important increase. I mean, I'm not saying it's negligible, absolutely, because you don't have to think only to flooding. I mean, in terms of flooding, we are not talking about, we are not talking of big increases. If you keep in mind the order of magnitude, the amplitude of sea waves, they are much higher than 0.63. And so in terms of flooding is not really a huge risk. But in terms of saltwater intrusion, which is very relevant to water resources management, is quite a significant increase. But again, we are not talking about meters. These predictions are done by climate models. Climate models, on the one hand, we know that they are uncertain. On the other hand, note that climate models, I mean, they may not consider some tipping points because they are based on our understanding of the physics. There might be some dynamics that lead to tipping points that we don't know. So we cannot say that the prediction by the climate model is precautionary. Absolutely not. It may be not conservative, not precautionary, if a tipping point occurs. And this is what basically oceanographers or climate scientists say. They say if you get a sudden release of water from the Greenland, then you may get an increase of sea level suddenly in a relatively short period of a couple of meters. This is what they say that may occur. So these predictions don't take into account what we don't know. Okay, I think we can stop now for 15 minutes. We make the long break, so I take a coffee. If you have any question, please. I saw that, Ludovica, you had a question about the exam date. There will be any in July? Yes, it's not yet fixed. And the reason why I didn't fix it is that I wanted to wait a little bit to see if there is the possibility to make the exam in physical presence. I think it is very unlikely. So I think we can also fix the date in July. The last news from the ministry say that it's very unlikely that before summer we can go in physical presence, and I don't think it is likely. And maybe in September. I'm not sure even in September, but okay. If you have any other question, please let me know. Very good. Okay. So this is about sea level. Just 1 second, I check that you see everything. I hope you can still see the screen. If there are any problem, please let me know, because for some reason on the phone I don't have the connection, but I think you should have. Okay, so now for the sea level, I think this is the conclusion, and so the important thing to keep in mind is the order of magnitude of what we already observed and the order of magnitude of the predictions. The predictions which, however, don't take a tipping point into account. Just 1 second. Okay, yeah, now it's okay. So now let's turn into the discussion of the climate change impact on the water cycle. Okay, I see. There is the screen that is not shared. 1 second. Okay. Okay. Give me only, okay, I want to see the chat. Can you please write on the chat if you see my screen? I'm sorry, but I need this confirmation. Now not, okay. So let's see what happens. Okay, now. Let's see. I don't understand why it looks like it's not visible. Just 1 second, I try again. So okay, now let me see. It is really, I don't understand why I can't share the screen. Let me. Okay, let me try to change the connection. Give me 1 second. I will get disconnected for just 1 minute. Sorry for that. Let me see. Okay, here I am. Now let me try to share it again. Can you please confirm to me if you see my screen or not? I guess not, but just give me a confirmation. Oh, now you see it, correct? Okay, perfect. Okay, so, okay, I think it was a problem of connection. Let's see. I hope that it works, but now I can change it, so no problem. Okay, so climate change on water cycle. This is the next one. We discussed so far precipitation and sea level. Now, what I want to discuss is to discuss the river flow. And so let's focus on the Po River. And again, here the purpose is to look at observations. And then later we will discuss about climate models. But if we look at observations, let's take the example of the Po River, and I go down to the figure that you should see in a while. Let's wait a little bit. Now you see it. This is it's an animated figure. So animation is going a little bit scattered because of the connection. But if you look on the website, you see a continuous animation. And it's the max annual river discharge. And this is a daily series. So every year I took here and I connected with the dark line the yearly max of the daily flows. It's in cubic meters per second First of all, look at the order of magnitude. It's about 10,000 cubic meter per second, the max of the daily flows. Now, if you look at the whole picture, forget about the moving line for one moment. Look at the picture, at the red line. If you look at the picture red line, you don't see any relevant change. You see up and downs, which is normal, but you don't see any relevant change. Indeed, if you fit a regression line over the whole series, it's more or less horizontal. It's interesting to fit a regression line on pieces of this series that are 50 years long. And this is what is done through this animated line that goes through the picture. And if you do this exercise, first keep in mind that 50 years, it's quite a long time. Usually for climate analysis, when we have 50 years of data, we are very happy. Now, given that this series is very long, we can repeat this exercise many times. The exercise of fitting a regression line over 50 years. And if you do it with a moving regression, you can see in blue the times where you get a slope that is upward, so increase. In red, you see the times when you get a decrease. Actually, you see up and downs, and keep in mind that there is no consideration of the significance of the regression here. So when you see that the regression is almost horizontal, it means that it's a small change, which is close to zero. Here, anyway, when it's close to horizontal, is colored in red and blue. But you see that there is indeed an up and down, and there are cycles. So again, even for river flows, you don't see a big change. We are talking about floods here. You don't see a big change over the whole observation period, and you see cycles. Okay, very good. Now, let's look at other examples, and let's look at larger scale. There was a recent review by, I am selecting it, oops, sorry, I clicked on the link, by Hall et al. It's a bit slow, just one second. I selected it. Yeah, now you see the selection. It's an open access paper, and this review analyzed, let's say, assessed the output from several studies on individual catchments. Basically, in the recent past, there have been a lot of studies like the one on the Po River that I did, which is showed here. A lot of studies which referred to individual catchments, and this paper, Hall et al., makes a review of these studies for Europe, and here are the results. If you divide Europe in regions, and you look at the regions which are depicted here in the legend, Western Europe, Northern Europe, Central Europe, you see the arrows up and down, which synthesize the results of previous studies. So in some regions of Europe, depending also on the scale of the catchment, there have been detected increasing trends, in other regions decreasing trends. And you can see indeed a pattern. Increasing trends in the Alps and over Central Europe, decreasing trends in the north of Europe, increasing trends in Ireland and Great Britain, decreasing trends in the south of Europe. So this is, again, based on the results of previous studies. Basically, what comes out is that there is heterogeneity in the results. And as I said, it depends also on the scale of the catchment. Now, this is, as I said, a review. And recently there were studies that were done for Europe on the magnitude and seasonality of floods. These are two important studies. One was published in Nature and the other one in Science. And they were based on a database that was put together, which is very interesting and relevant. It's a database of floods in Europe. And what they found is that there is a change in seasonality, and change in seasonality meaning that here there are no details, but there is the link to the paper. Here it's mentioned. Change in seasonality meaning that in some places where floods are fed by snowmelt, there is an anticipation of the flood season, and this is consistent with global warming and also reasonable. There was another recent study, which is not mentioned here in Science, as I said, which I had the opportunity to co-author, but actually it was really a major effort by several research groups in Europe, and which focused on the magnitude of floods in Europe and found that in the north of Europe floods are increasing, in the south of Europe are decreasing. Actually, there is to say that these studies refer to large catchments, so they are not representative of small catchments. So the picture that comes out from flood analysis is again an heterogeneous picture. The changes are not very relevant, by the way, but what we can see is that there is a change in seasonality and changes that depend on the climate. There is not a unique pattern, what I mean, and therefore the conclusion is that if you have to make a design in a specific place, you have to be very careful to consider what are the patterns that were detected for the region you're working in, and be sure that the results that you use to support your analysis are consistent with the scale of your catchment. Now, droughts. Droughts, we already said that it's a complicated story, and there is no convincing proof that the drought frequency is increased under global warming. What is important to say is that recently there were indeed important droughts that were observed around the world. Here there is a list which is not complete, and I have to complete this. And for instance, here I mentioned the drought in California. The drought in California, I'm sure that you heard about it. It lasted about 4 years. It was officially closed in 2017. And the Millennium Drought in Australia. This is another example of a drought that lasted for several years and lasted from 2001 to 2010, officially closed in 2011. Other examples, a drought in South Africa lasted 4 years, from 2013 to 2017. Another example, a drought in Athens, lasted about 4 years, 1996-2001, more or less. So these were phenomena that were indeed catching the attention of water resources managers. And the reason is that they lasted for several years. And then came to a closure, which was something that was not really expected. Like in Australia, after 10 years of drought, they thought that this was something that was changed forever. But actually in 2011, Australia was hit by a series of abundant years in terms of precipitation, and therefore they had the opposite problem of being flooded rather than being affected by droughts. And it never came out again, a so long drought in the last 10 years. So what came forward is that indeed we have to be concerned by these multi-year droughts, which seems to occur in several parts of the world. So now a question could be, is the frequency of these multi-year droughts increased recently? Actually, after experiencing these events, we try to look back in the sequences of precipitation and river flow, and we saw that even in the past, we observed frequent, or let's say we observed several multi-year droughts. It's a phenomena that we still don't know, and it's coming to the attention of researchers and scientists now. So, what is the reason for these multi-year droughts? Can we predict them? Are they related to global warming? A first analysis seems to show that these droughts are not really, the frequency is not increased under global warming, but the period of global warming is still too short to reach a final conclusion. So I want to show you a couple of figures which are not included here. And first of all, how can we look at droughts? We can look, for instance, if we consider again the Po River, we can look at the minimum rather than the maximum annual river discharge, again measured in terms of daily river flow. And if we look at the progress of the series of the Po River, again, we don't see overall a tendency. If we fit a regression line, it goes up and down. But we can see that there are some periods, multi-year periods of low flow, one around 1940, the other one after 2000. And so I think it is interesting to try to look at the sequences then, at the sequences of years where we found a sequence of low flows. And if we do this exercise, let me try to open another picture. I hope I can find it very soon. Let me see. For instance, this is precipitation in Bologna. Precipitation in Bologna, it's daily precipitation in Bologna, and it's a long series. It started in 1813. So let me see if this is the figure I was looking for. This is the daily series, so it doesn't say anything to us. So let me close it. But let me now see the annual series. Here is the annual series. Let me enlarge it. Still, here you can't really see the sequences of drought. And now let me refer to another figure where I identified the droughts. Here they are. Okay, this is another figure where I identified with the gray color the multi-year sequences of rainfall below average. This is annual rainfall. Annual rainfall, and when I identified years below average with a duration of more than 5 years, I identified them in gray. And you see, if you look at the time scale, let me show it. Here you can see the time scale. You see that these multi-year droughts are occurred, it seems, more frequently in the first period of the series and more frequently during the period 1900-1960. This is for Bologna rainfall. Let's look at the Po River now. And so Po River, 1 second, it's here. I think it is this one. Yes, it is this one. Let's look at the time scale. For the Po River, you see that indeed we see, first of all, the series start from 1920. So we see in the beginning of the period some droughts, multi-year droughts, up to 1960, then a lower frequency, and then there is the drought of the 2000s. So again, it doesn't look like there is an increased frequency recently, but still, I mean, under global warming, the length of the data sample is short. And then there is, again, the question that may come out. So what is the cause of these multi-year droughts? And how can we predict them? Is there a way when we observe 1 year of river flow or precipitation that is below average? Is there a way to anticipate if it's part of a multi-year sequence or just one? This is the big question, and this is something that is really open for research now. And it looks like something that always occurred, but still it's unknown. Okay, let me go back to the web page then. And again, probably it's the fact that multi-year drought are occurring is due to the Earth-Kolmogorov effect, probably. But again, this is a matter of research. And I am also involved in part of these researches because I am making a consultancy activity now for the ERA, which is the water manager in Bologna, and they are concerned that a multi-year drought may occur. And then we are trying to understand what is, first of all, if the frequency is maybe going to increase in the future, and what are the predictors that we may use to anticipate these droughts. Because, you know, if a drought is 1 year long, basically we are prepared against it. Our recent experiences around the world have shown that if it's a 1 year event, we are getting prepared. We know how to make our water supply system resilient with respect to a 1 year drought, but we still don't know how to make ourselves resilient with respect to a multi-year drought, because if you have reservoirs, for instance, they get into a crisis if it's a multi-year drought, because if they are not replenished during winter, then it's a problem. And also, if you rely on groundwater is like a reservoir, and it takes time to recover after a drought. If the drought is long-lasting, it's maybe a problem. Okay, and this is what is our perspective on the observations for the hydrological cycle. The conclusion that we may get from the observation is if we look at the hydrology, there are cycles. There are events that occur in sequence. There might be exacerbated. Their intensity may be increased under global warming, but still our knowledge is too limited to reach conclusions. And what we have to take into account is that indeed these extreme events may occur, and no matter if they occur because they are due to the global warming or they are not, but they occur, and we have to get prepared to them. Now, climate models. Climate models is another way of inspecting climate change, and the assumptions, we already discussed them. They are based on the knowledge of the physics. They give rise to projections that vary depending on the scenario and depending on the model. Different models make different assumptions. Some of them consider some feedbacks, some of them not, or some of them consider other feedbacks, so their projection change. Look, in climate science, they use the term projection, not prediction, to make clear that it is not something that we should use as a prediction, because a prediction the term prediction implies implicitly that you have some certainty, and for this reason they don't want to use it, and they use projections. Now, there are two considerations that I would like to make about the climate models. The first consideration is the fact that they are affected by uncertainty, and people know that. Also, climate scientists know this. There is a lot of research ongoing on reducing the uncertainty of climate models. There are plenty of studies. enormous funding dedicated to that. So it's not a mystery that there is uncertainty. Most of these studies aim to discover and model feedbacks that we still don't know. Now, the awareness that there is uncertainty leads climate scientists to devise solutions to estimate it. And the solution that they usually use is the fact that sorry, I'm taking a note for something that I want to say later and that I don't want to forget. The method they use to estimate uncertainty is to perform simulation with different models. So they know that each model is uncertain. They know that some models rely on assumptions that other models don't consider, but because they consider other assumptions. Their reasoning is, by making an ensemble of simulations, I estimate uncertainty. Because, of course, I mean, if you combine several uncertainties, you get an overview of the overall uncertainty. And this is usually the way they present their simulation, like the figure that you see here. Different models, they more or less agree with the observations because some of them were tuned over the observation. So they more or less agree up to now, but when you predict the future, they diverge. And by assessing the divergence, the range of the predictions, they estimate uncertainty. Actually, there is an important thing to note that by comparing the output of several different models, actually, we are estimating not really model uncertainty. We are estimating the range of the predictions, which is a different story. Because if you take into account that models can be all wrong, and for sure they are all wrong, because there is uncertainty in each of them, then it's clear that the range of their prediction may not encompass the true value. So the range of their prediction is not an estimate of uncertainty. The good estimate of uncertainty should encompass the true value. But what kind of assurance do we have that the range of these models encompasses the true value? We don't have this. The only way to estimate the uncertainty of a model in a statistically correct way is to compare models with observations. And this is something that is not done usually in climate analysis. It's not done because usually models fail to reproduce the current climate, and therefore they cannot rely on this because they say that climate models are not conceived to simulate the current climate. So this method of comparing models with observation is not used, but actually, statistically speaking, it's the only way to estimate uncertainty. This is the way we use in hydrology. In hydrology, we compare models with observations, we calibrate them with observations, and then based on the error in calibration, we estimate uncertainty. And this is not done here. Uncertainty are presented as a range of predictions again. And this is something that you really have to take into account, no matter what is your opinion. I mean, we are not concerned here of who is right. We are just concerned to use for our design an information that is reliable and with uncertainty that is correctly estimated. And with correct, I mean that the uncertainty band should encompass the true value. And in this way, we are not sure of that. This is the first consideration that I wanted to make. So beware of the fact that when you are given an uncertainty for climate models, you have to learn how it is estimated. So this is the question that you should ask yourself. And this is always what I do when I read papers. I get an estimate of uncertainty. I look in the paper how it is estimated. So this is one thing that you have to always keep in mind. The second consideration that I wanted to make, and I took a note not to forget it. And then I'm close to closing the lecture. Sorry if I took some more time. Second consideration, there is a different view between people that use inductive and deductive methods for assessing climate change. So people who use inductive methods, they look at the data, as I did before, and try to estimate from the data if there has been a change, and basing on the change that is eventually detected, they try to predict the future. This is typically the approach of engineers, because engineers, they want to rely on data, usually. They want the data because they think that if they go in front of the court because they made a mistake, it's easier to convince a judge by showing data than showing a model output. So usually engineers use data. And this approach is criticized because data are uncertain, they have a reduced coverage. We discussed these issues. I said precipitation is difficult to monitor. We don't have data on heavy precipitation. So this is the criticism that is moved against this, against the inductive approach. On the other hand, the deductive approach is more, gives to you the opportunity to make a prediction based on the physics. The criticism that is moved to the deductive approach to climate models is precisely what I just said, that uncertainty is not rigorously estimated, cannot be, maybe, and therefore the engineer is a bit reluctant because the engineer says that, it's something that is not really reliable. And I think it is very important, no matter what is your opinion again, to keep in mind the pros and cons of the two approaches. And just to give you an example, I had a discussion with a he's a brilliant climate scientist. His name is Filippo Giorgi. He's working in Trieste in Italy. And he showed some model predictions for future extreme rainfall a couple of years ago, and demonstrated that future extreme rainfall is going to increase a lot under global warming. And then I asked him the question, and as I said, he's brilliant. I said, if these predictions are true, why didn't we observe in data up to now an increase in extreme precipitation under 1 degree of warming? And he said, the data are not certain. There is uncertainty in that. And I replied, okay, I see your point, but what about model predictions? They are uncertain as well. And he concluded by saying, I know, but still it's something that we have to take into account. It makes use of our knowledge of physics. And I fully agree. We have to use models. The only thing, we have to be aware of the limitation of one approach rather than the others. Okay, and then let me conclude by saying one thing. There is a way to couple the two approaches. There is a way to do that. And, it's a way that is known from a long time. So I presented this way in several papers that I recently co-authored. And there is a reluctancy by some scientists to use this method. The method is simply called stochastic simulation, which means a statistical technique that takes into account the physical basis. I don't want to go into the details, and because it's something that is too detailed for your needs and also for mine. But what I want just to say is that it's indeed a way, there is the way to make a fusion of data analysis and model simulation. There is a way, and it is well known since a long time ago. There is a bit of reluctancy because, the problem is that if you estimate uncertainty in a correct way, you end up with an estimate that is very large. Uncertainty bands are very large, and this is why some people are reluctant to adopt this approach, because some people think that if we give a transparent overview of the uncertainties that we still have as researchers, we lose credibility. So some people, when they present their results, they don't present uncertainty bands because they think that in order to convince the public that climate change is a urgency, you just have to pretend that there is no uncertainty in the predictions that you make. I can understand the motivation. I'm not criticizing it. I just want to inform you that there is this convincement, especially in climate scientists, and engineers have a different perspective, and I tell you why. There is the convincement that if you present uncertainty in a transparent way, your message loses its credibility. On the other hand, the engineer is concerned by another thing. The engineer is concerned by the failure of its design. And therefore, the engineers want to get an estimate of uncertainty, because the engineer knows how to deal with uncertainty, with safety factors, with other decision-making processes. The only thing that the engineer needs is an estimate of uncertainty, reliable, not. And as I said, when you go in front of the court, it's easier to convince a judge with data analysis than with a modeling exercise, because or if you use a modeling exercise, you have to prove that your model is correct, is reliable, and the way to prove that it's reliable is estimating uncertainty. So we end up again with data analysis. Now, this is the final part of my lecture, and there is a discussion on climate change mitigation and adaptation. This discussion is very descriptive, and especially mitigation, very descriptive. Please read it independently. And adaptation is again another descriptive section, but I suggest you to pay particular attention to adaptation, because adaptation is the task of the engineer. So just have a look at these suggested strategies for climate change adaptation that you read here. I will not ask at the exam anything about these, but have a look, because I think it is interesting. Most of them are, already, but they are interesting to have an overview of what could be solutions for climate change adaptation in water resources management. I think it is important. And just have a look at it. There is also a discussion on stochastic simulation, which I already mentioned. Again, I'm not asking anything at the exam, and I kindly ask you to read it independently. And you may take an inspiration for maybe a concluding presentation on that. And keep in mind that when we talk about design of climate change adaptation strategies, you don't find guidelines. You don't find technical guidelines. It's something that it's a task for you. A task for you to estimate what could be the future climate, to get an idea, to estimate uncertainty, and to translate your knowledge into technical design. Okay, I think I took too much time, so I just would like to close, but I remain at your disposal if you have any question. Okay, and very good. I think you are still all here, so thank you very much for attending. And if you have any suggestion on how to improve this lecture, which is a work in progress, and I really would appreciate it. Okay, thanks students. Ciao, see you on Monday at 9 o'clock. Bye bye.